Hello and namaste everyone. Welcome to lecture 13 of this NPTEL course on stochastic approximation. So let's do a quick recap of what we did in the previous two lectures. In the last but one lecture, we looked at martingales and some examples of martingales, and also looked at the connection between martingales and martingale difference sequences. In the previous lecture, we looked at two specific things. One of them was constructing a super martingale from an existing one. In particular, we said that suppose xn is a super martingale and cn be a pre-visible process, then the process yn, which is defined in this way, is also a super martingale. Apart from this, we studied something called as the Doob's upcrossing lemma. It is one of the fundamental results that is used towards proving convergence of martingales. So this result stated something like this. It said that suppose xn is a super martingale. Further, suppose this variable un subscript ab, okay, be the number of upcrossings of ab within the time window 0 to n, right. Then the Doob's upcrossing lemma said that this inequality holds. Okay. So what does this inequality say? B minus a times expected value of un ab is less than equal to expected value of xn minus a minus. Okay. So as I said in the previous lecture, what is nice about this result is that un of ab in some sense tells you how many times did the process xn, okay, did an upcrossing of the interval ab between the time window 0 to n. So notice that in some sense un of ab depends on what happened between the time what happened during the time interval 0 n, whereas the right hand side only concerns the value of the stochastic process xn at time n. So in other words, Doob's upcrossing lemma connects what happened in the time window 0 to n to the value of the process at time n, right. That is what is nice about this result, and these are the two things that we discussed in the previous class. In today's class, we will look at convergence of super martingales by building upon these results that we saw previously. So towards this, one of the first things that we will be studying is this corollary 11.4. Again, this number corresponds to a result in this textbook called as Probability with Martingales by David Williams. So in case you want more details, you can actually refer to this textbook and look up this result over there. Okay. So what this result says, in particular this result says something about the number of upcrossings of a super martingale. So this result says that suppose xn is a super martingale that is bounded in L1. Okay. So there is a L superscript 1 over here if it is not clearly visible. Okay. So we have a super martingale that is bounded in L1. So when I say we have a super martingale bounded in L1, I would imply that a condition like this holds. So let us look at this condition. Okay. If we just had expected value of absolute value of xn is less than infinity, then we will use that to conclude that your xn is integrable. Here we are saying something more. We are saying that the supremum of expected value of xn is less than infinity. That is, we are not just saying that every xn is integrable, we are also saying and importantly saying that the supremum of these expectations is finite, right. So let us presume that such a condition holds for the given martingale, given super martingale. Furthermore, let us presume that there are two real numbers a and b such that a is strictly less than b, and let us define u infinity of ab to be the limit of un of ab. So let us decipher this notation a bit. You can see that there is a up arrow here, right. So what does this up arrow mean? Okay, so what does this up arrow mean? Well, u n of AB in some sense looks at the number of up crossings in the time window 0 n, and it is easy to see that un of AB will be less than equal to un plus 1 of AB. In particular, for any omega in capital Omega, un of AB of omega is some integer and un plus 1 AB of omega is another integer, right. And what we are saying is that the number of up crossings in the time window 0 to n will be less than the number of up crossings of the interval AB in the time window 0 to n plus 1. So, this is obvious to see. So, this implies that your UNAB as a function of n is actually a monotonically increasing sequence, and because it is a monotonically increasing sequence, the limit actually exists for every little omega, and hence there is a limit in terms of the random variable itself, and let us denote the limiting random variable by u infinity of AB, right. So, u infinity of AB, I hope you are able to see, is again some function from omega to r. Okay. So, what does this result say? This result says that suppose you have a supermartingale which is bounded in L1 and you have real numbers a and b such that a is less than b, then your u infinity random variable satisfies the following relation. In particular, b minus a times expected value of u infinity AB is less than the absolute value of a plus the supremum of expected value of absolute value of xn, where the supremum is taken over the index n, right. And we have been given that this supremum is less than infinity, right. Furthermore, we have been given that a is a real number, which implies the absolute value of a is finite, and putting these two facts together, we can see that this plus this will also be finite, right. So, what this result says is that if you have a supermartingale that is bounded in L1, then b minus a times expected value of u infinity of AB is less than infinity. So, let us try to understand what is u infinity of AB. Well, as you may have already guessed, it is the number of up crossings of the interval AB over the window from starting from 0 and going all the way up till infinity, right. So, that is what u infinity of AB is, and this result says that the expectation of this random variable, which counts how many up crossings you have over the entire 0 to infinity window, is actually less than infinity, right. And because this is a non-negative random variable and b minus a is finite, your expectation is finite, and because this is a non-negative random variable, from the definition of expectations, one can easily see that this fact implies that the probability that u infinity AB takes the value plus infinity is 0. In other words, your u infinity of AB is less than infinity almost surely. That is what we can conclude from this fact. Okay. So, we are now going to prove this result. Okay. So, let us go about proving this result. So, from the result that we saw in the previous class, in particular from Doob's upcrossing lemma, we can conclude that b minus a times expected value of UNAB is less than equal to expected value of xn minus a minus, right. And separately, one can see that xn minus a minus is trivially less than absolute value of xn plus absolute value of a, right. And if you are a listener hearing this lecture, please figure out why this inequality holds, right. And the hint is that it is a consequence of triangle inequality, right. And since you have absolute value of xn here, right, we can take the supremum over all possible values of n, and to distinguish between this n, I have replaced the index as k. So, this absolute value is less than this absolute value. Okay. So, there is typo over here, this expectation should not be there. right. So xn minus a minus is less than absolute value of xn, and that is less than supremum over k of absolute value of xk plus absolute value of k, right. And because you have this inequality over here, right, you have this inequality over here, right, we can take expectations on both sides to conclude that b minus a times expected value of un ab is less than supremum of k greater than equal to 0 expected value of xk plus a. Okay, so there is a small typo that I made, right. Actually what I should say is this inequality over here, okay, this inequality over here actually implies expected value of xn minus a minus is less than equal to expected value of xn plus absolute value of a, and then one can actually conclude that this is less than equal to this, right, and from this one can conclude that because this relationship holds, b minus a times expected value of un ab is less than equal to supremum of expected value of absolute value of xk plus a, right. Now because this relationship holds and u infinity is a monotone limit of un's, we can invoke the monotone convergence theorem on the one hand to conclude expected value of u infinity is the limit of these expectations, right, and because each of these expectations is upper bounded by this, we can then conclude that b minus a times expected value of u infinity of ab, right, this is less than this, and because of the given condition that your xn supermartingale is bounded in L1, one can conclude that this is less than infinity to finally infer that b minus a times expected value of u infinity ab is less than infinity as desired, right. So recall that we wanted to show this part, right, and we have shown that part. Okay, so the key idea is to use this monotone convergence theorem to relate the expected value of u infinity to expected value of un and connect expected value of un to the supremum of these expected value of absolute values of xk, right. So we can conclude this, and then as I said, since this is a non-negative random variable and its expectation is finite, we can conclude that the probability that u infinity of ab equals plus infinity is actually 0, right. So what does this mean? Okay, so let us try to give a physical interpretation of this statement, right. So it means that if you have a supermartingale that is bounded in L1, right, so the sup of these expected value of absolute value of xn is less than infinity. So if that is the case, then the number of upcrossings of this interval ab in the infinite time window from 0 to infinity, okay, the number of upcrossings being infinity has 0 probability, which means that with probability 1 the number of upcrossings will be a finite number. Okay, so of course on different sample paths or different sample points omega, the number of upcrossings could either be 100, 500, 5 trillion or any big number. However, what this result says is that with probability 1 this number of upcrossings will be a finite number, right. So this finishes one of the key results that we would be needing to discuss the convergence of supermartingales. We will now use this result to prove the convergence of supermartingales. In particular, this result is known as the Doob's forward convergence theorem, and the forward over here refers to the fact that we are looking at what happens as the time index n is taken to infinity in the forward sense. Okay, so that is what forward over here means. Okay, so what does Doob's forward convergence theorem state? It states that suppose you have a supermartingale which is bounded in L1, so that the previous corollary that we discussed applies, right. So bounded in L1 means this condition. Then Doob's forward convergence theorem says that almost surely the limit of the supermartingale exists, right, and is finite. Is this okay? So almost surely the limit exists and is finite, right. So this is what is the convergence theorem. So what it means is that if you have a supermartingale that is bounded in L1, then with probability 1, if you look at the limit of your supermartingale, right, the limit will be a finite number with probability 1, right. So again this notation over here means that your x infinity of omega is defined to be limit n tending to infinity xn of omega. Okay, so that is what this limit this definition means. Alright, so now let us see how the previous corollary can be used to prove this result, and this result is actually a very clever application of real analysis, and hopefully you will enjoy it the way I also enjoyed it when I read it or saw it for the first time, right. So we want to show that almost surely the limit exists and is finite. So we will break the proof into two parts. First we will show that the limit exists, and then we will show that the limit is actually a finite number, right. So towards showing that the limit exists, what we will do is we will first define a capital lambda set, or which is an event which consists of all those small omega for which your sequence xn does not have a limit, right. And when I say does not have a limit, it does not have a limit in this extended interval minus infinity to plus infinity, which means that we are also not claiming that your xn's could actually go to plus infinity, right. So that convergence is also we are presuming not holding, right. So this event, it is very easy to see from some basics of real analysis that this limit is equivalent to this limit. So it basically says that lambda is the collection of all little omegas such that the lim_inf is strictly less than the lim_sup, right. So those who have seen limits of real numbers or real sequences of real numbers know that the limit is said to exist only when the lim_inf is equal to the lim_sup, and we also know that the lim_inf is always less than equal to lim_sup, and hence when we say the limit does not exist, it is equivalent to saying that the lim_inf is strictly less than the lim_sup, right. And what we are going to do now is we are going to break down this event into a union of some very interesting events, right. So we will break down this event as a union of events which are indexed by A and B, where A and B are some rational numbers with the property that A less than B. So what is lambda AB now? Lambda AB is the collection of all those omegas where the lim_inf is strictly less than A, and A is strictly less than B, and B is strictly less than lim_sup. Okay, so let us try to understand what we are doing over here. Because your lim_inf and lim_sup have this strict inequality relation, I hope you agree that we can squeeze in two real numbers A and B such that this relation holds, right. So we are saying take all these omegas and break it up into this union so that whenever this inequality holds, right, you can find two numbers AB such that this inequality holds, right, and you can put all of them together, right. And notice that I am not saying this union is a disjoint union, so some of the omegas could overlap multiple lambda ABs. It does not matter. What matters is that this set of rational numbers is a countable set, and hence this is a countable union. Okay, so that is the key part, right. So now from our previous corollary we know that this random variable with probability 1, right, takes a finite value, or this random variable u infinity takes the value infinity with probability 0, right. And lambda AB, which is defined over here, my claim is that is a subset of this event, right. So let us try to understand why this subset relation holds, right. So lambda AB says that lim_inf is less than A and lim_sup is bigger than B, right. And from the basics of real analysis we know that a lim_inf of a sequence is a point which is infinitely often visited by xn, right. So or more generally or more specifically, right, any neighborhood of the lim_inf of a sequence is visited infinitely often, right, by that sequence, right. And from that observation, and also a similar conclusion for lim sup, that is any neighborhood of lim sup will also be visited infinitely often by the sequence. One can see that if you visit this neighborhood infinitely often and some neighborhood of this infinitely often, and if you choose the neighborhood so that that neighborhood is below A and the neighborhood of this lim sup is above B, one can conclude that because these neighborhoods are visited infinitely often, the upcrossings of AB will be plus infinity, right. So for every omega that belongs to lambda AB, one can conclude that on those omegas the number of upcrossings of the interval AB will be plus infinity, that is you will have infinitely many upcrossings of the interval AB, and you will have this infinitely many upcrossings because you will infinitely often visit a point below A and you will infinitely often visit a point above B, right. So that is the reason, and hence one can conclude that lambda AB is a subset of this. And in the previous corollary we have seen that the probability of this event is 0 for any AB, right, and hence one can conclude that probability of AB must be 0, right. And from this and the fact that your set of rational numbers is countable, one can conclude that probability of lambda itself is 0, right. So what is lambda? Lambda is the set of all omegas where the sequence xn does not have a limit, and what we have managed to show is that probability of lambda is 0, which means that this event has 0 probability, and hence the complement of this event which says that the limit exists has probability 1, right. So that is what we have written over here, that x infinity, which is defined as limit xn, exists almost surely in this extended interval minus infinity to plus infinity, right. So I am working with this extended interval. So extended real line basically means that you also allow x infinity to take minus infinity and plus infinity. So we are allowing that at this point because you could also have a scenario where your xn's take larger and larger values and hence their limit would actually be plus infinity, right, and so on and so forth, right. So now in the result though it states that the limit exists and it is finite. So we have now shown that the limit exists, and now it remains to show that the limit actually is finite almost surely, okay. And in order to prove this second part, we are going to make use of another very important result from probability theory, which is referred to as the Fatou's lemma, right. So I am going to state this Fatou's lemma, right, but I will not be proving it, but I will tell you how one can go about proving this result, and those who are interested in knowing about the proof of Fatou's lemma can refer to theorem 5.3.2 and corollary 5.3.2 in this textbook called as a probability path by Resnick, okay. So what does Fatou's lemma say? At a very high level, Fatou's lemma relates to the expected value of lim inf of xn and the expected value of lim sup of xn, right. So let us try to understand what Fatou's lemma says. So Fatou's lemma says that suppose xn is some sequence, okay. So for Fatou's lemma you do not need a Supermartingale or any special property of this sequence. All we require is that xn be some sequence of random variables with the property that all xn's are lower bounded by z, okay. So again when I write something like this, I actually mean that xn of omega is greater than equal to z of omega for all omega in capital Omega, right. So we require this condition. So suppose xn is a sequence of random variables such that xn is greater than equal to z and z is some random variable in L1, which basically means that your expected value of z is less than infinity, right. So the setup is that we have a sequence of random variables which is lower bounded by an integrable random variable z, and z can be arbitrary, right. So if such a setup such a random variable exists, then one can conclude that the expected value of the lim inf of xn is less than equal to the lim inf of expected value of xn. So notice that lim inf over here is applied on xn, right. So which basically means that this is the random variable which on sample point omega, okay, is the liminf of xn of omega, right. So this random variable at omega is basically taking this value. Now xn of omega will be a sequence of real numbers, and liminf for sequence of real numbers always exists. So this liminf is always well defined, right, and by invoking your monotone convergence theorem, one can conclude that the the expected value of the liminf also exists, right. And what this Fatou's lemma says is that you can interchange the liminf and the expectation. So the result says that the expected value of the liminf is upper bounded by the liminf of expected value of xn. So notice that in this Fatou's lemma, z does not appear anywhere in the result, right. So that is very nice, right. It in some sense, in the language of chemistry, acts like a catalyst, right. So its presence is needed for this inequality to hold true, but as such it does not play any role in the result, right. So this is what Fatou's lemma says on the liminf side, and there is a similar outcome on the lim sup side. So the result states that suppose you have xn less than equal to z, right. So in the liminf case, notice that we wanted xn greater than equal to z, whereas in the lim sup case we require that xn be upper bounded by z, and z again is required to be L1 integrable, right. Then one can conclude that lim sup of expected value of xn is upper bounded by expected value of lim sup of xn, right. And if you combine both these relations together, we can conclude that if your absolute value of xn is upper bounded by z and z is integrable, right, which implies that minus z is less than equal to absolute value of xn, sorry, minus z is less than equal to xn is less than equal to z, right. So this thing holds, allowing us to apply both parts of Fatou's lemma. We can conclude that your expected value of liminf is less than liminf of expected value of xn, and for any sequence of real numbers we know that the liminf is less than equal to lim sup, and from the second part of Fatou's lemma we know that lim sup of x, so I should say lim sup of expected value of xn, this is from the second part of Fatou's lemma, sorry, from the second part of Fatou's lemma we know that this inequality holds, that is lim sup of expected value of xn is less than expected value of lim sup of xn, right. So this is what is in some sense the broad conclusion of Fatou's lemma, that is if xn's absolute value is less than equal to z for every n and z is integrable, then expected value of liminf is less than liminf of expected value of xn. Now this is less than equal to this from a standard fact of sequences of real numbers, which says that liminf of a sequence is always less than lim sup, and this second inequality or the third inequality again follows from the second part of Fatou's lemma, right. So I am not going to prove this result, however those who are interested, okay, I encourage you to try proving it yourself, and I am going to only say that it is a very easy consequence of monotone convergence theorem, and those who need some additional help, I suggest that you look up this textbook by Resnick called as probability path. Alright. Okay. So now what remains to show is that this x infinity is a finite random variable, and it takes a finite value almost surely. Is this okay? So how can we invoke Fatou's lemma? The way to invoke Fatou's lemma is to make use of the fact that your absolute value of xn is greater than equal to 0 for all n greater than equal to 0, right. So this 0 over here is playing the role of z, and hence from Fatou's lemma one can conclude that expected value of liminf of absolute value of xn is less than the liminf of expected value of absolute value of xn. Is this okay? Now in the first part of this proof we have already shown that the limit exists, right, almost surely, And furthermore, we know that this absolute value function is actually a continuous function. We can conclude using these two facts that this holds, right. So in other words, your absolute value of x infinity is equal to absolute value of limit n tending to infinity xn, and now this just follows from definition of x infinity, okay, and from this one can conclude that this is equal to this, and this follows from the continuity of the absolute value function. Is this okay? And because the limit exists, the limit of this is equal to the lim_inf of this. Is this okay? So that one can easily show, right, and one can then use this fact that absolute value of x infinity is this, right, and we know that lim_inf expectation is less than the lim_inf of expectations, to conclude that expected value of absolute value of x infinity is less than lim_inf of expected value of absolute value of xn. So we are just putting this over here and using these facts over here to write this left hand side, right, and we have one can trivially see that lim_inf of expected value of xn just from the definition of lim_inf is upper bounded by the supremum of expected value of xn's, right, and the supremums of expected value of absolute value of xn is presumed to be less than infinity, because we have presumed that your sequence xn is bounded in L1, right, and we can use all these facts to conclude that your expected value of absolute value of x infinity is less than infinity, right, and we can use the definition of absolute value of x infinity, right, to conclude that by using the definition of expectation of non-negative random variables, one can now conclude that a relation like this holds, because if this probability had a positive value, then that would immediately imply that expected value of absolute value of x infinity is infinity. Now since we have shown it is strictly less than infinity, it can only happen when this probability is 0. Now because this probability is 0, we can conclude that your absolute value of x infinity is a finite number almost surely, right. So on different omegas, x infinity can take different values, right. So sometimes it can take 5, sometimes it can take -100, and as large a number as you can imagine, but what we are saying is that the set of omegas where absolute value of x infinity is plus infinity, okay, that has probability 0. Okay. So with this I come to the end of this class. Let me now summarize what we have discussed in this class, right. So as I told you, in the analysis of stochastic approximation algorithms, we have to understand the behavior of noise, right, and in the first week during the discussion of the first week, I told you that the noise in stochastic approximation algorithms is typically viewed as a Martingale difference sequence, right, and a Martingale difference sequence is in some sense a difference of a Martingale sequence, right, and we will later on see that we will use the convergence of Martingale processes to show that the cumulative effect of noise in a stochastic approximation algorithm is negligible in an asymptotic sense, right. So that is the relation between what we are studying or what we studied today to how we will be using them in the study or analysis of stochastic approximation algorithms. So let me quickly summarize what we did today, right. In today's class we looked at convergence of supermartingale. Since a martingale is a special case of a supermartingale, whatever we have studied today also applies to martingales, right, and we showed that one of the sufficient conditions under which a supermartingale converges is that of the supermartingale being bounded in L1, that is the supremum of expected value of absolute value of xn is less than infinity, right, and the key ingredient that was used to show this convergence result was the Doob's upcrossing lemma. With this let me stop. Thank you, namaste. I hope to see you in the next class.